Anyone else talking? That's it. So what were we discussing? So last class we started with Lorentz force, right? So what does it state? If you have a magnetic field existing, okay? In this magnetic field, if you have a charged particle which is projected, then what happens to this charged particle? It starts experiencing how much value? Q into B vector cross B vector. So F vector is equal to Q into B vector cross B vector. Right? So then I told you when you write it in the scalar form, you write it as QEB sin theta, or F vector will be equal to QBB sin theta times n cap. Correct? So these are all the concepts that we discussed. And I told you, if velocity is 0, then what will happen to the force? It is going to be 0. Whereas, if theta is equal to 0 degrees or 180 degrees, what will happen? Velocity need not be equal to 0, but force will be equal to 0. So, what is the difference between force 0 in this condition and this condition? In the first condition, you say that the charged particle is at and here you will say that the charged particle is in uniform motion. Right? These are all the concepts that we have already discussed. Correct? Now, so first point is we'll see the special cases. Listen to this carefully, this is very, very important. We'll see special cases. Okay. First is, what if theta is equal to 0 degrees or 180 degrees? This we already saw. So that is what I already gave you. What is going to be the answer? So you have magnetic field and you have a charged particle and it is given a velocity v. Okay. If theta is equal to 0 degrees or 180 degrees, what is going to be the force on the particle? It is 0. Means what will you say? Particle continues to move with this we have already written, but still write it down. This we have discussed. Particle continues to move with uniform motion. What is the meaning of uniform motion? Okay. Acceleration is 0. Means it moves with uniform speed or velocity, whatever we call it. Correct? Right? The next one is, what happens if theta is equal to 90 degrees? Okay. Second case is, what if theta is equal to 90 degrees? Listen to this carefully. Let us say I have magnetic field which is being directed into the plane of the paper. Okay, this is the direction of whom? This is the direction of magnetic field. Means the magnetic field is like this, right? Students, those who are online, are you able to hear me?
Yes, sir.
Yes, sir.
Yes, sir.
That's clear, right? Okay.
Yes, sir.
So this is the direction of magnetic field. If I take a charged particle and project it exactly perpendicular to the magnetic field, what do you think will happen? If I project it perpendicular to the magnetic field, will it experience force in this scenario or not? Yes, it will, because I'll revisit the equation. My first is I'm not concerned about vector. I'm concerned about the magnitude of it. QVB sin theta, where theta is the angle defined between the velocity vector and the magnetic field, correct? So if theta is equal to 90 degrees, then what will be the value you substitute here? So obviously sin 90 is going to be 1. So QVB is going to be the force, which is definitely a non-zero value because the particle is charged. So Q is not equal to 0. Velocity of the particle is not 0 because we projected with some velocity, and the magnetic field is also existing, right? But here, the tricky part is, concentrate. As soon as this particle enters this magnetic field, I repeat it, listen to this carefully. It's a very important one. Based on this concept, there is a device XII Physics. I'll tell you. Okay. So there is a charged particle projected perpendicular. As soon as it enters the magnetic field, what is the first thing that you will be able to observe? It experiences a non-zero force of how much magnitude? QVB. That we have concluded. But now, we need to be concerned about the direction in which the force is going to get exerted on this particle. So how do you know it is on? So when you do the cross product, we know that F vector is equal to Q into, what is it? B vector cross B. It is not B cross B. Okay? Be very careful. It is B vector cross B vector. So velocity vector is in this direction. Magnetic field is in this direction. So what are we? How are we supposed to apply the right hand thumb rule? So from the first vector, curl your fingers towards the second vector. But what is the important point there? In the shortest direction possible. When I have to do that, this is V vector. I'll curl my fingers into the plane and extend your thumb. This is going to be the direction of force. So in this scenario, as soon as the particle comes here, the velocity vector will be like this, and the force vector will be like this. Accepted. Right? So velocity is still like this, force is still like this. Now tell me one thing. Since this particle is experiencing a non-zero force, can I say that the velocity of this particle will change? Listen to my question carefully and answer. I'm saying this particle is experiencing a non-zero force of Q into V into V. According to Newton's first law, when the particle experiences force, it can no more be the condition of rest or an uniform motion. Means it needs to accelerate. Accepted. Correct. So in this case, the charged particle will accelerate, right? But that is wrong. Why? There is one more important point you need to think about. See, my job is to confuse you. You have to think and answer the question properly. I gave all the hints. I told everything. What did I say? Particle moving with a uniform velocity, when it experiences force, will accelerate. Is that statement correct? Yes, it is correct, provided the force acted in the direction of velocity. That's what Newton's first law told. unless and until there is a force applied on an object in the direction of its motion or in the direction opposite to its motion. But what is happening here? Velocity is like this, but the force is perpendicular to the velocity. Now, another important question is this happening only at the instant it has started entering the field? Think about it. This is where the basics of your cross product of vectors comes into picture. So, what does cross product of two vectors tell us? If you do cross product between two vectors A and B, then the resultant of it is always in the direction perpendicular to both the vectors for which you are doing the cross product. I repeat it again. If you are doing cross product between two vectors, the resultant is always in the direction perpendicular to whom? Both the vectors for which you are doing the cross product. Correct? If that is the scenario, velocity is one of the vectors and magnetic field is the other vector. So I can conclude throughout the line in which this particle is going to be within the magnetic field and the velocity is going to be perpendicular to the magnetic field. Force is always perpendicular to velocity in this scenario. Am I clear with that point? Is there any point that is confusing? Because I have asked so many questions. Is there anything that is confusing or is there anything you want me to explain again? Anything that is unclear? I told two important points. What are they? Though the force is a non-zero value, though the force in this scenario is a non-zero value, particle does not accelerate. Okay, this is first point. What about the second point? Since F vector is resultant of whom? B vector and B vector. Correct? So resultant of B vector cross B vector. Sorry. Then what I can say is F vector is always perpendicular to B vector and B vector. Accepted. Correct? So, keeping these 2 points in mind, let's try to understand what happens to the charged particle in this scenario. So, can we say that respect to y-axis? Because what happens here is this force, it is not making the particle accelerate, rather it is only used to change the direction of particle. That was the next question I was about to ask. Okay, this force is a non-zero value, but velocity is still there. You're saying the particle still continues to move with uniform velocity. What is the previous scenario I gave you? Theta is equal to 0 degrees or 180 degree. Right, when I say theta is equal to 0 degree or 180 degree, I told force acting on the particle is 0 and velocity is uniform. Means the particle continues to move in the straight line path. Accepted. Now, in this case also, the velocity is still going to be uniform because the particle is not experiencing force in the direction of velocity. It is experiencing only the direction perpendicular to velocity. But does that mean, like the previous scenario, this particle will still continue to move in a straight line path? Think about it. What will happen to it? It will start moving in a curved path. But the most important point is what curve is it going to take? What shape is it going to take? So it starts moving like this. Are you at least in agreement with me in this context? It's that. So what is the force doing here? It is not accelerating the particle, but it is only changing the direction of the path. Sorry, it is changing the path of the particle in which it was moving. So it starts taking a curved path. Correct? It does change direction. Not necessarily. You tell me what is the kind of motion where the direction of particle will change, but still it has uniform velocity. That's a scenario, right? This is a centrifugal force, but it is, and I'm asking, it is not accelerating. That is what I asked. particle does not accelerate in the direction of velocity. Means the velocity is still, what I'm trying to tell here is, the velocity is still going to be constant. That is a very important point you need to make a note of. So what is happening here? The third path is telling us that this velocity component and force component are always perpendicular to each other, and there is only one kind of motion where this kind of scenario can take place, and that is called as uniform circular motion. So what happens in this context is the particle will start moving in a circular path. So most of us would have thought, how many of you guessed parabola? You would have thought that it doesn't take the parabolic path, rather it takes a circular path, and in the circle also what is going to act, what is the only acceleration it will have? It is only centripetal acceleration, there is no tangential acceleration acting on the path. Is that clear? So the conclusion is, since F vector and B vector are always perpendicular to each other, particle moves in a, someone speaking? Those who are online, is anyone speaking?
Yes.
The particle moves in a uniform circular motion. Right? Is this clear? So having all this data, we need to derive what would be the radius of the circular path in which this particle will revolve. Shall we try finding it out? Repeated. We need to find what is the radius of the circular path in which this particle is going to revolve. So what is R? How to find it? So when a particle is in circular motion, what is the only force acting on it? Force acting on the particle is m into v square divided by r. Correct? It is m into v square divided by r, which let me call this as 1. Okay. Sorry. Force acting on the particle, can I call it as q into v into b? Magnetic force, right? So I'll call this as magnetic force acting on the particle is q into v into b accepted. Let me call this as equation number 1. Similarly, what is the centripetal force acting on the particle? Centripetal force acting on the particle is mv square divided by r. Let me call this as 2. So, is this magnetic force not the one which is providing the necessary centripetal force? Correct? Magnetic force is always directed towards the center because force and velocity are perpendicular in this scenario. So this force is what is the centripetal force? 1 is equal to 2, which implies q into v into b is equal to m into v square divided by r. V and v are gone. So what can you say about r? R is equal to mv divided by qb. So this is going to be the radius of the circular path in which the particle will revolve. Okay, this is a very, very, very important expression. Please make a note of it. Is it clear? Right? So those who are online have completed it. Yeah.
Yes, sir.
Yes, sir.
Any doubt? Is there anything not clear or any other point you want me to explain again? Okay. So theta is equal to 90 degrees delta. So what are the two special angles we took into consideration? For two special cases, 0 degree and 180 degree and 90. Now what will happen if the charged particle is projected at any angle other than these two cases? Theta is not equal to 0, 180 or 90 degrees. What will happen in this scenario is what we are going to see. Is it clear? But sorry, I missed one thing. Sorry, before you write this, right? Sorry about it. So I told you the radius of the circular path, right? How much is the radius we took into consideration? So R is equal to mv divided by qb, where m stands for what? The mass of the charged particle. V is the velocity of the charged particle. Q is the charge of the charged particle, and B is the magnitude of the field. Correct? Now, how much time will it take for the particle to complete one revolution? What is the time period of this particle? Right? So next question we need to ask is, what is the time period of the particle? So time period is equal to distance by speed. So what is going to be the distance? If we cover a distance of 2 pi r in one revolution divided by v. So 2 pi into what is the value of r? It is mv divided by qb, the whole divided by v. Accepted? So v and v are lost. So this will be 2 pi m divided by q into v. Let this be the time period. So what can you conclude from here? That the time taken by the particle to complete one revolution in the case of circular motion. I repeat it, guys. This is not with respect to the third scenario. This is the continuation of the second scenario. Okay, please write this off and write down this point as a continuation of the second scenario. So the time period of the particle is 2 pi m divided by qb. Correct? This is not there. Okay. So previous scenario, I'm still continuing. Okay. 2 pi m divided by qb. Correct? So from here, what I will conclude is, observe one term is missing. So time period of particle is, what can I say? Independent of the velocity. Is anyone speaking? So those who are online, are you clear?
Yes, sir.
Okay.
Yes, sir.
So time period is independent of the velocity of the particle. But if I write the same thing in terms of frequency, what is frequency, guys? 1 divided by capital T. So 1 divided by T means, can I call this as QB divided by 2 pi m? So what is this QB divided by 2 pi m called as? This is what is called as cyclotron frequency. Cyclotron is the name of a device. Okay, write it down. It's called cyclotron frequency. CYCLOTRON, cyclotron frequency. Okay. So these are the three expressions you need to remember when they ask you about circular motion. What are they? Because if you take any point, right, and I didn't say it is acting upward. Listen to my statement. I told it is always perpendicular to velocity. So once it takes a curved path, for any kind of a curved motion, the velocity of the particle will always be tangential to it. So when it is tangential, what will be the component which is perpendicular to a tangent? Normal. A normal will always direct itself towards whom? Towards the center. That is why you see at every point, right? If this is velocity, this is the normal. So if there is a motion where the force is always directed towards one point, that one point is what we call it as the center, and that kind of motion is called as, more specifically called as uniform circular motion. If you just answer and say it as circular motion, it is still wrong. Why? Because in circular motion you can have a non-uniform motion also. What do you mean by non-uniform circular motion? This is also changing. So in a uniform circular motion, what will happen is velocity will remain constant, but direction will change. But in non-uniform, velocity will also change, direction will also change. See, I'm just mentioning all these points because in case study they can ask these kind of questions. If at all it is there. Okay. Wash it. Fine. You're good. Can I love this? Next. Third is the third point we need to discuss. When theta is not equal to 0, 180 or 90 degrees. When this is going to be the scenario, observe. If this is the direction of magnetic field, okay, and if the charged particle is given a velocity like this, right, where it is making an angle theta with respect to the magnetic field. In the previous scenario, what did I do? Magnetic field was drawn into the plane, but here I didn't draw it into the plane, rather I drew it in this way. Okay, so once it starts entering the field, what will happen? So once it starts entering the field, even before it enters, right? Let's say this is just before it has entered. So when it is entering, there is a V sin theta component acting in the direction of magnetic field. Sorry. V cos theta. So there is V cos theta component acting in the direction of magnetic field, and V sin theta component acting in the direction perpendicular to the magnetic field. That's it. Now, what will V cos theta being parallel to magnetic field do? So V cos theta is parallel to V. So when velocity and magnetic field are parallel to each other, what will happen to? So can I say F is equal to 0? Correct? Whereas V sin theta is perpendicular, is always perpendicular to V. So what can I conclude from this? So force is QVV, and here what is the most important point? So due to this force, the particle will be in uniform circular motion. It will be in UCM, uniform circular motion, accepted. So V sin theta is a component of velocity which is responsible to put the particle in circular motion. So what will happen in this scenario is the particle will be like this, no? It will go into the plane and come out of the plane. So if you see from this side, it will be in this way, right? So it should have actually been like this, right? But in the previous scenario, what I did is the field was drawn into the plane. Okay. Now what will happen? If you see from this side, the particle will be in a circular motion in this form. Okay, it means it will go into the plane and come out of the plane, into the plane and come out of the plane, right? But when it is happening, right, this V cos theta component, which is a non-zero value, will not keep the particle in a constant circular motion. Rather, it will try to push the particle. try to listen to this carefully. Had this v cos theta not there, only v sin theta existed, the particle would have been in a circular motion like this. Right? It will go into the plane and come out of the plane. But this v cos theta component will try to push the particle because v cos theta is the one which is responsible for the linear motion of the particle. So what will happen in this scenario is the particle will no more be able to be in a continuous circular path nor a continuous straight line path. Rather, it will have a combined circular and straight line path, which will have path like this. Which has a path like this, and this path is what we call it as helical path. So it's called helix. Okay, this is what is called as helical path. So it goes like this, comes out like this, goes like this, and comes out like this. It keeps on traveling. Okay. So here, what will you say? Who's responsible for the circular motion? V sin theta. Who's responsible for the linear motion? V cos theta. Okay. Now there are some important terms we are going to derive from this course. It has. Maybe my diagram is bad, but it has a fixed state. It has a fixed radius, and this distance is also uniform. Okay, is this clear? Right. Now the question is, what is going to be the radius of the helical path? So, what is the radius of the helical path? So, if you look at the previous formula, we had mb divided by qb, correct? So, here can I use the formula mb divided by qb? I cannot use it. Rather, I can use it if I make a small modification. What is the modification I need to make? I need to write it as v perpendicular into v perpendicular divided by qb, because the perpendicular component of velocity in this scenario is the one which is responsible for the circular path. So what will happen here is m is the same in the place, so it becomes v sin theta divided by qb. Now observe this is a very important point. If I put theta is equal to 90 degrees here, will it become the scenario of previous case? If I put theta is equal to 90 degrees, it will become previous scenario, right? So when I put theta 90, mathematically what are you going to get? mb into sin 90 divided by qb. Sin 90 is 1. So I have to wait. Will you not get mb divided by qb? So which was the previous expression that we already derived? Are you able to understand? So this is what happens. So this is like a special case also. Okay. Is it clear? Now, so this is going to be the radius of the helical path. And most importantly, we need to see what is the distance traveled by this particle in one time period. Okay. So, if the particle started here, okay, if the particle started here, when the particle goes into the plane and comes out of the plane, in one time period, can I say there is a shift of this much value? Means if this is 0, exactly after one time period, where can you find the particle? At point A. After the next time period, where will you find the particle? At B. So are you in acceptance with the fact that for every time period or every revolution of it, the particle is getting drifted by a small value? Right? This drift is taking place. Now our job is to find what is the magnitude of the drift. Okay? How do you find it? Can I rub this? Right? So we know the time taken. So how much is the time taken by the particle to go from O to A? So time taken by the particle to go from O to A. Time taken by the particle to go from O to A is one time period, which is equal to 2 pi m divided by qb, correct? But in this time period, in this time, Who's pushing the particle along the horizontal direction? It is v cos theta. So OA, can I say it is speed multiplied with time? So what is the speed of the particle? It is v cos theta into the time taken by the particles 2 pi m divided by ub. So what are you going to get? 2 pi mv cos theta divided by q into d. So this is the horizontal drift that has taken place to the particle due to v cos theta. And this horizontal drift is given a special name called pitch. PITCH. Okay. So when will this concept arise? When will the concept of pitch arise? When the particle is projected at an angle other than 0, 180 or 90 degrees. So if they tell you by default that the particle is moving in a helical path, this should come to your mind. And when the particle is in a helical path, it definitely has a non-zero pitch associated with it. Is that clear? Theta is 90, by default you will. Any doubt, guys? Those are online, any doubt?
No, sir.
Yeah. So why I use cos theta is because in the direction from O to A. Okay. Somebody asked me why. Shubham asked me why are you using cos theta in the place of sin theta? So if you observe, when you go from O to A, right? Yeah. So when you go from O to A, it is v cos theta component that is acting in this direction, right? So this v cos theta multiplied by time is a scalar quantity. So v cos theta multiplied the amount of time it takes for the particle to go from O to A will give you this distance. And that distance is this value. So v cos theta multiplied with time is 2 pi m divided by qt. Then you solve it. And this value OA is what we called it as pitch. Is it clear?
Yes, sir. Thank you,
Is
sir.
it clear?
Yes, sir.
Okay. Can you rub this? So open your textbook. There are some problems based on this. We'll try that. Yeah. So go to page 137. Page 137. Example 4.2 at the bottom. 4.1 that is rod. 4.2 only, no. So what is given there?
The magnetic field is parallel to the positive y-axis. And
Magnetic field is parallel to the positive y-axis.
charge particle is moving along the positive x-axis.
The charged particle is moving along the positive.
Which way would always force be for an electron negative charge?
So this is B vector. So if there is an electron that is projected in this direction, what will be the direction of force? It's a very simple thing. So what they are asking is, F vector is equal to Q into V vector cross B vector. So Q into what is V vector? V I cap cross B vector is V J cap. Okay. What about Q? It is minus Q. Okay. So if it E into D into what is I cross J? K. And a negative sign is there, it's a minus K. So the particle will start moving into the plane of the sphere. So this would be the direction of force experienced by the charge particle. It will be into the plane of the field. Is it clear?
For positive charge.
For positive charge, it will be in the opposite direction. So you can use right hand thumb rule and find it out. V vector from V, if I need to curl my fingers towards V, I go in the anti-clockwise direction, extend the thumb. So this is the direction of force. Had it been a positive charge, had it been a negative charge, it would be in the opposite direction.
Why
So-
is this that?
Because you are not changing the sign of Q. You're doing only V cross V, but you never took the sign of Q into consideration. So by default, you are assuming it to be positive. Correct? Huh? So whichever is easy, you can go. I go with this method. So shall we try the next example?
If we use Q, we find it at the
Theta will be 9. But that's of no use. Because QVB sin theta will only give you magnitude, but in this question, they clearly ask you about direction.
So, theta is 90 degrees after.
So here, still the particle will be in circular. So circular motion will be like this. So electron will go into the plane, take a turn, and come out of the plane. A positive charge will come out of the plane, take a turn, and go into the plane.
We should say the answer according to
Not origin, you can just say it will come out of the plane and go into the plane. It will be in circular motion. But since they didn't ask you, we need not worry about it. Provided they ask you, okay,
then both are chemical.
you have to mention which direction first. Yeah. Let's try 4.3. Yeah. So example 4.3. How to solve this? Read the question. Then read and try. What is asking in 4.3?
Is
So what is the data given?
what is the radius of the path of an electron? It's of mass 9 into 10 to the power minus 21.
31 and
Yes. And charge 1.68. Moving at the speed of 3 power centimeters. And magnitude
3 into
10 to the power 7.
okay.
The magnitude field of 6 into 10 to the power. Yes.
Everything is in standard unit. Okay. So did they give you that the charge particle is moving in the if it's projected perpendicular to the magnetic field? Okay, then you know it is going to move in a circular path. So you know the formula already, R is equal to NV divided by QV. All the data is given, take and substitute it here, that will be answer. Is it clear? Okay, this is a simple problem.
What's this?
Frequency is how much? Frequency is equal to QT divided by 2 pi n. So Q is known, B is known, 2 pi is known, B, M is also known. You can substitute it. Right?
energy in electron volt.
So calculate the kinetic energy in electron volt.
K
K is kinetic energy.
kilo electron.
Kilo electron volt. KE you are saying. Okay. I thought they are asking you the kinetic energy in terms of electron. So kilo electron volt, right? It's 10 power 3 eV. Okay, can I rub this? So I'm assuming calculation part you guys can do it. Okay. Now, what is the kinetic energy this particle is going to have? Kinetic energy is half mv square. So you know the mass of the particle, you know v square. Calculate it. Okay. And the answer will be in terms of kilogram meter square per second square, which is also known as joule. Which is also known as joule. So remember, 1 electron volt is equal to 1.6 into 10 power minus 19 joule. Same. That's what I wrote it as QB by 2 pi. We derived it, no, the cyclotron frequency. It's the same thing. 2 pi R, yeah, you'll again write it as MD by QB only. So write down this one. 1 electron volt is 1.6 into 10 power minus 19. Why is it so? Listen to this. If I have 2 points, okay, listen to this. If I have 2 points A and B, between which 1 electron is moved, okay, and the potential difference between AB is 1 volt. I repeat it. The potential difference between the points A and B is 1 volt, and you have an electron, and this electron is moved across a potential difference of 1 volt. Then what will be the amount of work done by us? Work done is equal to Q into VAB. You remember this? So Q is how much? It is the charge of an electron, and VAB you call it as 1 volt. So 1 electron volt is this much value, 1.6 into 10 power minus 19. So if somebody asks you to define it, you would say it is the amount of work done to move an electron across a potential difference of 1 volt. Write it down. What is 1 electron volt? It is the amount of work done to move whom? To move an electron between a potential difference of 1 volt. Clear? Now can you do the conversion? So they ask you to convert it from 1 joule to 1 kilo electron volt, right? So whatever answer you get here, this half mv square divided with 1.6 into 10 power minus 19. So this will give you the value in terms of electron volt. Okay. Then again, from here you will have 10 power minus 3 left out. Take the 10 power minus 3 through the numerator, it becomes 10 power 3. And the 10 power 3 electron volt is what we call it as kilo electron volt. Are you able to understand? So by the way, what is the value of kinetic energy they got from here? You can check the textbook and everything. Joule how much?
4 into 10 power minus.
So 4 into 10 power divided by 1.6 into 10 power minus 19. So this goes 0.4 times. So 1 divided by 0.4, or I can write it as 10 by 4, right? 5 by, so 2.5 into, it goes to the numerator, 10 power 3 electron volt, so it should be 2.5 electrons. Other 2.5 to 10 power electron volt or 2.5 kilo electron. Okay. Next. Amount of work done to move an electron across a potential difference of 1 volt. Right? So this is all about what happens when the charged particle is projected into magnetic field. Here, now we will see what happens when a current carrying conductor is placed in magnetic field. What will happen? When a carrying current carrying conductor is placed in magnetic field. Suppose I take the magnetic field to exist in this direction, and in this we have placed, let's say, a current carrying conductor of length L. Okay, we have placed a current carrying conductor of length L. And let's say the current is flowing in this direction. Okay, then in what direction do the electrons tend to move? The electrons move in this direction, and the electrons have a drift velocity of v. Correct? So generally, when you talk about a conductor carrying current within it, then the electrons will start moving with an average value of drift velocity. That's what current electricity told us. Correct? So when this is going to be the scenario, then what is the force experienced by one electron? So this E is not the electrostatic force, it is the magnetic force experienced by electron. How much? E into V, or I will write it like this: E into V vector cross V vector. I'll go with cross product because I don't know the angle. So let's say this is the axis. This axis is making an angle theta. When I say the axis is making an angle theta, what will happen to the velocity of this particles? The velocity of the velocity component is also making an angle theta with the magnetic field, except correct. So E into V vector cross V vector. Now having this in mind, I will write V as L vector divided by T. Okay. Cross, I am leaving it as V vector. So this is also the force experienced by an electron. Correct? Or if you see, if you can ask me, sir, why not minus sign? You will put it. If n electrons are present, if n electrons are present, then the force experienced, the total force will be how much? It will be minus n into E into L divided by T vector cross T vector. This T will come out. It's a scalar quantity. So can I write it as minus NE divided by T into L vector cross B vector? What is this N into E? Quantization of charge. It is the total charge that is flowing inside the conductor. So the total charge per unit time will give me the value of current. So here the minus sign has something to do with the negative charge of the electron. So the whole thing I will call it as current, and L vector cross So this is going to be the force experienced by the conductor. So what happens is when a current carrying conductor of length L is placed in a magnetic field B, then the force experienced by the current carrying conductor is given by the expression I into L vector cross B vector. Okay. L is length. So you can take it in the direction of current or in the direction of velocity. So since L vector is taken here, I took it in the direction of velocity. That is why I wrote it as L vector by D. That's fine. See, okay, if at all you want to take L vector, if that is the case, take it in the direction of current itself. So what I would suggest is this L vector, we have taken it in the direction of BD, right? So what we can say here, this you can put a minus sign here. So according what he is asking is, why can't we take I in the direction of L? So if you take, L vector in the direction of current. So if you take it like that, velocity and current are in opposite direction. So L, then what will happen to the velocity? This is B vector, this will be L vector. Then I can write it as minus L vector divided by T. So this minus of minus also you can combine and write it as plus, and then this NE by T will become I into L vector cross B vector. See, this is not the standard derivation of it. This is just an explanation of how to derive the experience, the force experienced by the charged particle with the help of Lorentz. Because we never ask the question, how is the charged particle going to move? It is going to revolve in a spiral path or anything of that sort. That's not what we are trying to talk about. Current carrying conductor is that if you have a wire, that current is flowing, you take that and put it in magnetic field. One thing you can observe is start moving. And why is it moving? Because there is a magnetic force experienced by it, and its value is I into L cross. Clear? So that is one thing. I into L vector cross B vector, or this can also be ILB sin theta times n cap. So here also one important point is to be noted. What is it? The force experienced by the current carrying conductor will be perpendicular to both L vector and B vector. Okay. So it is ILB sin theta in times n cap again in terms of vector, or you can simply write it as ILB. Are you able to understand this? This is what happens, right? So this is all about the force experienced by the current carrying conductor based on external matter. After the first step, you go to and in the second step, ordered minus velocity is displacement by time. Yes, sir, by ordered minus because velocity is in the direction opposite to L vector. So I took L vector as the direction of current. So if this is the direction of L vector, velocity is the direction. That is the meaning. Yeah, where? In this case, sir, for electron you need to take. So what we can say from this scenario is when you see this formula I into L vector plus B vector, you can say that L vector is exactly in the direction of current itself. That's it. Okay. That's it.
Sir.
So this is all about different kinds of forces that are existing. So in the next class, we'll discuss about torque. Then there are two devices that are left out. One is galvanometer and conversion of galvanometer into ammeter and voltmeter. Cyclotron is again deleted from your question. You don't have it. Okay. So that's it. Any other doubt? Yeah. So those are online. Any doubt is?
Sir, what you have
Sir,
written in
just
first
now
line?
what?
Sorry.
What you have written in first line, F electron is equal to minus E bracket. It is not visible, sir.
Not visible. Which step? This step.
Yes, sir.
I wrote that force experienced by one electron is minus E into B vector cross B vector.
Okay, sir. Thank you.
Okay. Yeah. So apart from that, any other doubt?
No, sir.
No, sir.
Any other doubt? Any other doubt, guys?
No, sir.
Okay,
No, sir.
then we can wind up.